Hi guys, this is Avisolterra, and today we're going to talk about how to find the position of a particle given the acceleration function, even when the acceleration function looks pretty complicated, like this function over here. So here's a sample problem where we'll get started. Suppose you've got a particle that's moving with this data that's given here, and we're going to find the position. And then we're also given these pieces of information. These are called initial conditions. Now before we get started, let's just review a little bit of pre-calculus that we're going to need later. Cosine of 0 is equal to 1. Okay, so remember that from back in pre-calculus. And sine of 0, that's equal to 0. Okay. So good. So that's just a quick review from pre-calculus. Now, working through the problem, remember that velocity, that's the antiderivative of the acceleration function. All right, so we can find out what the velocity function is by taking the antiderivative of the acceleration function. All right, and let's do that first. Okay, so the antiderivative of v of t, the velocity function, is going to be equal to the antiderivative of the first term, cosine of t. Antiderivative of cosine of t is sine of t. Then the antiderivative of sine of t is going to be negative cosine of t. Okay, plus some constant, and we don't know what that is. Now we're also given an initial condition. We could save it for later, but now's just as good a time as any. We've got v of 0 is equal to 4. Okay. We can solve for our constant by taking 4, plugging that in for v of t, and taking 0 and plugging that in for every occurrence of t. We get 4 is equal to sine of 0 minus cosine of 0, because remember we're plugging 0 in for t, plus c. Okay, and now here's where we're going to use our facts from earlier. Cosine of 0 is equal to 1, sine of 0 is equal to 0, plugging those in. 4 is equal to 0 minus 1 plus c. So that tells us that c is going to be equal to 5. Okay, so summing things up, we've found that v of t, if we take c and plug it back in, v of t is going to be equal to sine of t minus cosine of t plus 5. That's pretty good. That's our first step. What we can do next is to note that position, p of t, that's the antiderivative of velocity. So we can take our velocity and plug it in. We're going to find the antiderivative of sine of t minus cosine of t plus 5 dt. Taking the antiderivative there, we get that p of t is equal to negative cosine of t minus sine of t plus 5t plus some constant d. Alright, now just like before, we've got an initial condition, s of 0 is equal to 2. We can take 2 and plug that in for our position, and we can take 0 and plug that in for every occurrence of t. Okay, and I just noticed that I've been writing p over here even though I meant s for the position. This is the position function over here. Alright, so plugging these things in, we get 2 is equal to 0 gets plugged in for t, negative cosine of 0 minus sine of 0 plus 5 times 0 plus d. We're going to solve for d here. So we've got 2 is equal to negative cosine of 0. Cosine of 0, remember, was 1. So we're going to have 2 is equal to negative 1 minus 0 plus 0 plus d. So that gives us that d is equal to 3. So putting things together, since we found that d is equal to 3, then we can put that in our position function. P of t is going to be equal to negative cosine of t minus sine of t plus 5t plus the value we just found for d, which is 3. Okay, that just came from taking this and putting that down there. Alright, great work. So we found our position function here. There's our position function. And just to recap, what we did to find this position function was we took the antiderivative of acceleration to give us velocity. Then we took the antiderivative of velocity to give us position, and we used our initial conditions along with our knowledge of precalculus and trigonometry to use the initial conditions.